Hi, chemistry students. These notes are going to cover the groups of the periodic table and some of the information that we want you to know about them. It's also going to include some other information that's just kind of some fun trivia about different elements. There are a lot of very interesting things about them. And you're going to drag and drop parts of the notes into the spots that they go in as you watch and listen. So to get us started here, we have, again, our families and our periods, okay? So again, groups or families are going to be the vertical columns. So you'll notice those there kind of outlined in the aqua. And we have our group numbers there. So those have the aqua colored boxes around them. So just above lithium, we have the 1 there, and then so that's group 1. Group 2 is next to that. Group 3, 4, etc. through the middle there. And then we end up finally on the very far right side with group 18. We also have our periods that we talked about before. Remember, our period number is the same as the number of energy levels of electrons. And so those periods are the horizontal rows going across. Just like we would write a sentence with a period at the end, we write that sentence horizontally. And so we have, again, period 1 up there with hydrogen and helium, and then period 2 from lithium, and then it goes over to neon, period 3 from sodium over to argon, and then so on and so forth. So we want to talk a little bit more about valence electrons. Okay, so these are some specific electrons that we have. And so you can see here from our diagram, sodium has this 1 valence electron. And those valence electrons are the outermost energy level of electrons. Okay, so the outermost electrons there are the highest N value. Number N is telling us that period number or number of energy levels. And these are the electrons that are involved in chemical reactions. So that's why we're really going to pay attention to these electrons most from here on out, because they're the ones that act like the bumpers of the atom. They're the ones that run into other atoms and are changed in a chemical reaction. The valence electrons, we can figure them out based on the periodic table organization. And so the periodic table tells us the number of valence electrons by looking at the last digit of the group number. Okay, and so this is only going to apply to our tallest groups, like 1, 2, 13 through 18, but it's the last digit of the group number. And so again, if we look at our periodic table here, we had all of those period numbers here, but now we're going to talk about group numbers, okay? So the group number, like 1 here, would tell me the number of valence electrons. So everything in group 1 has just 1 electron in its outermost energy level. Group 2 has 2 electrons in its outermost energy level. Things here in the middle, though, don't follow the rules, so we're not going to have those any valence electrons that we're going to worry about for those. They kind of vary depending on which element we're looking at. Group 13 would just have 3 valence electrons, 14 would have 4, 15 would have 5, 16 would have 6, 17 would have 7, and group 18 would have 8. And so again, it's just that last digit of the group number that is telling us how many are in the outermost energy level for that particular atom. Now, there is one thing to mention here. Notice that helium is here in group 18. That should have 8 valence electrons, except for the fact that helium doesn't even have 8 electrons. So helium is going to be an exception to the rule because it only has 2 electrons total. So it can only have 2 valence electrons. So let's talk about hydrogen. And you may have noticed on our last slide and with our periodic table, we have hydrogen kind of set up there above the rest of the periodic table. And the reason that we have it set up there like that is because it doesn't really belong to any one group. A lot of times we talk about hydrogen belonging to really any group. And so it has some really unique properties. It has properties of both a metal and a non-metal. It can be a really poor conductor, but it also can be really reactive with halogens, just like alkali metals. Okay, so it's kind of like it doesn't act like a metal because it's not conductive, but it does act like a metal because it reacts with these halogens, which again, we'll talk about what those halogens are coming up. and what alkali metals are coming up in a second. It's very reactive and it is explosive with oxygen. And it is being looked at as an alternative fuel for cars. So they're looking at hydrogen fuel cells to use as a more kind of renewable or energy, so to speak. So let's talk about our different groups. Notice that we're going to talk about the alkali metals, which are group 1 minus hydrogen. Again, hydrogen is, even though it's shown above the group 1 elements, it's not really part of that group. And alkali metals are things that have this one valence electron. They are very, very reactive. They have very low densities, so they're usually, even though they're metals, they're very soft. Like the sodium that you see there in this picture, you can usually cut it with just not even a sharp knife in any way, just, you know, like a butter knife. They have very low melting points, meaning they are, again, very soft. They are good conductors of electricity, though. But they react really violently with water. And so when we take sodium and we put it in water, it will react really violently and actually burst into flames. And so you'll notice here, and along with in some other spots along the way in this presentation, that there are links in your slides. And so if you want to learn a little bit more about some of these things, you can certainly click on those links and learn a little more. So overall, we'd write this reaction then as Na for sodium plus water would produce that hydrogen gas H2 and then sodium hydroxide. And so sodium hydroxide is a base. Little trivia then, lithium has many uses, not only in medicine, but it's used to strengthen glass, it's used in batteries. Sodium gets its name from Latin, or sorry, its symbol from Latin, natrium, and it helps maintain water balance and nerve function, but too much can cause high blood pressure. So again, we have to be careful with that. We're not really talking about sodium in its elemental form, we're talking about sodium that is not in its elemental form anymore, and so it is not as dangerous when it's actually dissolved in our bloodstream. It's not like it's going to suddenly burst into flames in our bloodstream. There is a great video here of the government disposing of some sodium, big, huge containers of sodium into a lake after World War II. So if you are interested in seeing that and seeing some of the big explosions, you can take a look at that link there. Alkaline earth metals come next. That's our name for group 2 elements. And so these have 2 valence electrons. They are not as chemically reactive as alkali metals. However, they are still pretty reactive. They are harder than the alkali metals. And they are found in mineral ores. And that's why we call them earths. Okay, so mineral ores are sometimes called earths. They do still react with water to form hydrogen and a metal hydroxide, meaning basically a base, but they're not nearly as violent in their reaction as we see with those alkali metals. The transition metals come next, and that's that middle block on the periodic table. And so the transition metals are groups 3 through 12. These have their number of valence electrons varying, so there's no pattern necessarily here. They do have luster, meaning they are shiny. They are good conductors of electricity and heat. This is why things like copper, we use for wiring, and we use it for pots and pans in the kitchen. They do vary greatly, though, in their reactivity. They are found naturally in ores, so like iron ore, for example. So again, an ore is a mineral containing a relatively large amount of a metal compound. And some of them are magnetic. So iron, nickel, cobalt, those are examples of some of the magnetic elements. Little trivia here also, tungsten is used in light bulbs because of its really high melting point. So we can get it super hot and it will glow white hot, but it will not melt. Iron is what carries the oxygen in the hemoglobin in your red blood cells. And cobalt can be used as a blue pigment found in glass making. And so we can, make some really beautiful blue, dark blue glass with cobalt being put into it. Actually, interestingly, gold in glass will actually make a beautiful red glass also. Silver, silver is in jewelry and dishes, but did you know that silver also has some antiseptic properties? It can kill bacteria and fungus. So there's some great stuff in Innovation Nation here where you can learn more about that. So again, if you want to take a look at that, go right ahead. Our next group are the intertransition metals, which are also sometimes called rare earth metals. They're not all necessarily super rare, but they'd call them the rare earth metals. Big thing here is that these rare earth metals or elements are really, many of them, radioactive. So about half of them are found in nature and the other half are man-made or synthetic. Uranium, which is one of these elements, was used to make the first atomic bomb, which was called Little Boy. Okay, and so that's the top picture there. And plutonium, which is also a rare earth element here, is what was used to make the second atomic bomb, which was called Fat Man. And so that's the lower picture. You may not be able to really tell the size of those, but they are gigantic bombs. They are way bigger than you. So a couple of things also then, some interesting fun facts. If you look at the rocks here, rocks containing rare earth minerals like neodymium are widely used in electronics. They glow with exposure to an ultraviolet flashlight. And so this valley is at the base of a mineral complex in southern Greenland that is the site of a proposed rare earth mine. And so that you can see all of these rocks basically glowing when you shine this ultraviolet flashlight on it, and it helps identify all of those rare earth minerals that are rare earth elements that are there. Our next part that we're going to talk about are the metalloids. And so we talked about these a little bit before, but the metalloids are kind of along this stair-step line here. And again, they are things that are kind of sort of conductive. They're semiconductors. They have some kind of properties of metals and some properties of non-metals. So they're kind of these in between. And then on the other side of that, we have our non-metals. And so the next groups that we are going to look at kind of span between two different types of compound, or two different types of elements, from metal to non-metal to metalloid. And so we see a lot of differences as we go down the group in the properties of our elements. You will notice here that elements 113 to 118 are on your periodic table, but we don't technically know a whole lot about them. They actually don't survive for even a whole second. They're man-made elements that are very unstable, and so they will break down very quickly. So we don't really know a whole lot of their properties, only what we might be able to predict based on what groups they're in. So let's talk about group 13. Group 13 has 3 valence electrons. Again, just the last digit of that group number. Aluminum is in this group, and aluminum is a really low density, strong material. It is in rubies. Gallium is used in thermometers and light emitting diodes. The interesting thing about gallium is it is a solid at room temperature, but it has a melting point very close to that of the human body. Not the human body's melting temperature, but the human body's temperature. So if you put a piece of gallium in your hand, it actually will warm up just that little bit, and it will turn into a liquid. That TL there, and we kind of exaggerated that so you saw the L there. So the TL there is for thallium, and thallium is a possible carcinogen, meaning cancer-causing compound. It's really highly toxic. And so as we go down the group, we go from something like aluminum, which we use aluminum all the time, to something that's really toxic. Now, group 14 has 4 valence electrons, and this has carbon at the top of this group. It is the building block of life. And diamonds and graphite are 2 different forms of carbon, and that have really different properties. Diamonds are very, very strong. Graphite is very soft, and it's got these layers that will come right off your pencil and stick to the piece of paper. Silicon and germanium then are semiconductors and used in computer chips. And then, so found in transistors and solar cells. And then lead is toxic and causes brain damage. So, you know, again, we get huge differences as we go down our group here when we get over to the right side of the periodic table. Group 15 has 5 valence electrons. It has nitrogen at the top of the group, and nitrogen is an essential part of DNA, proteins, enzymes, things that make our body work. And it's about 80% of the air around us. Phosphorus is also in this group, and it is also an essential part of DNA, bones, teeth, ATP. But arsenic comes next, and it is poisonous. Okay, and antimony is below that, bismuth. None of those are particularly great elements, but especially arsenic is definitely poisonous. Group 16, we have 6 valence electrons. Oxygen is at the top of the group. It's the most abundant element in Earth's crust. Sulfur comes next. It is an essential part of proteins, and it's used to vulcanize rubber. So you can see in that top picture there, that white stuff coming out of the tree is actually sap from a rubber tree. So normally rubber is the sap, and you have to basically put it through a chemical process to turn it into something that becomes hardened enough to be a tire that you can use on your car. So that process is called vulcanization. And polonium then is at the bottom of this group, and polonium is a radioactive element, and it was actually recently used to kill a former Russian spy. So again, you can click on that link there if you want to learn a little bit more about that. So again, you can see here our abundance of elements in the Earth's crust. Oxygen makes up a huge part of that, not because oxygen is in its elemental state as a gas there, but because it's combined with all those other things that are there in compounds. And so, for example, silicon and oxygen combine to form silicon dioxide, which is sand. And so much of our Earth's crust is made up of sand. So oxygen, let's talk a little bit more about that. Oxygen can actually be made into different compounds. So ozone is one of those, and it is a molecule that consists of 3 oxygen atoms bonded together. It does have disinfecting properties, and so again, you can learn a little bit more about that and how it can be used to clean a gym bag there. Tellurium also has some interesting properties here. And so tellurium is a metalloid, and it is used in these CDRW and DVD-RW disks and in the data recording layer. But next, let's talk about halogens. So halogens are here in group 17. So even though astatine is in group 17, it's not actually a halogen because it's a metalloid. So again, when we get to the bottom of these groups, they get a little weird. So properties of halogens. Halogens are in group 17, so they have 7 valence electrons. They are very reactive. They usually combine with groups 1 and 2, so metals in groups 1 and 2 to form what we call salts. Halogen means salt former, okay? So just because we talk about salt doesn't mean that it is, salt that we eat. Salt is a general term in chemistry that we use for something that has really a metal and a non-metal that have combined together. Properties of halogens then. Fluorine is a colorless gas, although it's a super nasty gas, not one that you want to come in contact with. But the fluoride ion is something that is necessary to come in contact with. That fluoride ion helps us get healthy teeth. The iodide ion is needed for a healthy thyroid, and if you don't have that, it can lead to what's called a goiter. Basically, the thyroid gland there in your neck will swell up, and it kind of makes this big kind of bulge in your neck. And here's an example of what those different elements in the halogens look like. We have chlorine there. It's kind of a yellowish gas. We have bromine, which is this kind of brownish, reddish liquid. And then we have iodine, which iodine is a solid, kind of a grayish solid, but it will turn into a vapor pretty easily, and that is a purple gas then when it turns into a gas. One thing to note about chlorine is that chlorine was used as a poison gas in World War I, and so it is extremely dangerous. Bromine and iodine instead are not nearly as dangerous, and they are used for antiseptics, so like to kill germs and stuff like that. And so sometimes they may have used iodine dissolved in something, maybe at the doctor's office before a surgery, and it kind of goes on your skin very brown looking when they've dissolved it in oxygen in alcohol. Noble gases are group 18, and so helium is in this group, and helium, remember, is going to be our exception here. Helium has just 2 valence electrons because it only has 2 electrons total, but all of the rest in this group are going to have 8 valence electrons. The full outer energy level for all of these elements makes them very stable and unreactive. Okay, so all of these elements have a full outer energy level. They don't want to give their electrons away. They don't want to take more electrons in, and this makes them very unreactive. They are colorless, they are odorless, they don't want to react, and it's really hard, therefore, to find them. So it took a long time to find many of these elements in the noble gases. The noble gases are used for a lot of different things, from weather balloons to signs to photographic, like flash bulbs. They are, again, very unreactive and used to preserve historical documents like the Declaration of Independence. And again, there are a couple videos here that you can watch to learn more about those. Our last couple elements here, and what we'll really talk about here, is that we want you to color in your periodic table, or in this case, we're going to drag and drop our parts to color code our periodic table. And so again, we have nothing covering up hydrogen, but then we have our alkali metals in red. We have our alkaline earth metals in kind of the darker blue. We have brown covering up our transition elements. We have aqua covering up our rare earth or our inner transition elements. We have purple for the noble gases, yellow for the halogens, that bright green along the stair-step line for the metalloids there, and orange then for these other non-metals that exist. We'll leave the ones that are kind of under the metalloids, white, those are other metals that are not in the transition metals or those other special groups of metals, but they are metals. So you should make sure to, again, drag and drop those pieces into place, and check out some of those videos if you're interested. There's lots of great stuff out there to learn about the elements.